In this video, we're going to take a look at a problem like some of the homework problems that you'll encounter in this section. So here, we're going to have position as a function of time. Time is being measured in seconds. Position is being measured in meters this time. And I will just point out, I usually use P of t for position, and that's just because position starts with P. Your textbook is generally going to use S of t, and S is a very common name for a position function. I believe the reason for that is that there's some Latin word that starts with an S that means the same thing as position. You could also think of it as, hey, let's just use the third letter. I'm going to use P of t, but just want to point out that you'll very often see S of t used for a position function. Okay, now here we're not given a formula for the function, and we're not given a graph of the function. We're just given a table of values. And the directions say use the graph. We weren't given a graph, but we could generate a graph by plotting these points to estimate the instantaneous velocity when t is 1. Now, because I'm not given a full formula or a full graph of the function, the best we can do is estimate. Now, when you're asked to estimate something and you're checking your answer in the back of the book, it's okay if it's not an exact match, because you're estimating, and so you want to be in the right ballpark. You want to be close to the answer that's given in the back of the book. But if your estimate isn't exactly the same as the book's estimate, that doesn't necessarily mean you did anything wrong. If you're not sure whether what you did is close enough, feel free to email me or come to office hours or give me a call and just say, here's what I did. It doesn't exactly match the book. Is what I did right? And I'll let you know. Okay, so here's what we can do. Position is a function of time. So I'm going to put t here and P of t here. And I'm just going to plot these points. So let's see. I'm going to use a different scale on the x and y axis. It looks like I want to mark off every half second from 0 to 2. So this would be 0.5, 1, 1.5, and 2. And it looks like my positions need to go from -1 up to 7. So I'm going to use a slightly different scale here. 1, 2, 3, 4, 5, 6, 7 would be up here. -1 would be right about there. Okay. So I can now plot my points. I've got the point 0, 5, 0.53, 1, -1. Now, because I need to put that right about where I had labeled 1, I'm just going to erase that labeling and label the point 1, -1. 1.56, and then 2, 7. Now, there are a couple of ways that I could go about estimating the instantaneous velocity at time 1. I know that means the slope of the tangent line. I don't really have a curve here, but I could try and sort of draw in the simplest curve I can that passes through these points. So, there's a curve where I didn't introduce too much crazy stuff in between those points. That would be a curve that passed through those points. And then I could try to just draw in a tangent line and sort of estimate the slope of that. Okay. Now, I think that's what the book has in mind. But I'm not crazy about doing that, just because that's going to require that I draw things fairly well to scale. And I can do that. In this case, I wasn't super careful about this here, but I could certainly do that. These numbers aren't too crazy. But in a lot of applications, I'm going to have numbers that are very far apart, and I don't want to have to be worried about being super, super accurate with the scale. So what my other option is, and this is what I'm going to go with, is I can say, okay, I know that the instantaneous velocity is going to be the slope of the tangent line, but I also know that I can estimate that with secant lines. Now, if I were going to actually calculate it, I'd have to take secant lines using points that got closer and closer and closer and closer to time 1. With this information, I can't do that because I don't know what happens between 0.5 and 1. I can't get arbitrarily close to 1. These 2 points right here at time 0.5 and time 1.5, those are the closest I can get. But I could use those. I could say, okay, here's the secant line that I get using the closest point to the left. And I could calculate the slope of that. I'm going to just call that M1. M1 would be rise over run. So let's see, -1 minus 3 over 1 minus 0.5. I chose this as my ending point, that is my starting point. Okay, so that's going to be -4 over 0.5, which I can write as 1/2. So that simplifies to -8. And of course the units are just going to be the units on the vertical axis, which we said were meters, over the units for the horizontal axis, which we said were seconds. So the average velocity, which is the slope of the secant line, over that half second just before point time 1 is -8 meters per second. But I know I want to look both ways before I guess a derivative, or a slope of a tangent line, or in this case, an instantaneous velocity. So I'm going to also use the point to the right. I'm going to draw in the secant line using the closest point I have to the right, and I'm going to calculate the slope of that, which I'll call M2. Now again, that's just rise over run, so that's going to be 6 minus a -1 over 1.5 minus 1. So that's going to be 7 over 0.5, or 1/2. So that's going to be 14. And again, the units are meters per second. So that's the average velocity over the time interval from 1 to 1.5. If I want to estimate the instantaneous velocity at this time, I want to take into account what happened before that time and after that time. So I'm going to just say that the instantaneous velocity, I'm going to estimate it. So I'm not claiming that it's equal to this. I'm saying it's about. This is an estimate. I'm just going to average those. M1 plus M2 divided by 2. Okay. So that's going to be -8 plus 14 over 2. That's 6 over 2, or 3 meters per second. I think that's the simplest way of doing things that we can get from this table of values. Again, if I wanted to, I could just draw in a curve without making it too crazy, the simplest curve I can find that passes through these points, and then eyeball that. I would accept this answer with this work. I would accept a different answer if you had drawn in a curve and drawn in the tangent line and showed me that you were looking at rise over run for the tangent line that you had drawn in. So if you're estimating, there's more than one way of approaching things, and there's more than one correct answer to an estimate. Okay. Again, I think this is the simplest way, so this is generally how I'm going to try to work things out. But if you feel ambitious and you want to actually try to draw in a curve, make sure that you're drawing it to scale, and then draw in the tangent line, and then try to just measure the rise and the run, that's totally fine as well. And I believe that's what they've usually done in figuring out the answers that they give in the back of the book, which means if you do things by just averaging the slopes of the secant lines, or the average velocities over those time intervals, it's not going to generally exactly match the answer in the back of the book. So I just wanted to give you a heads up on that so that you don't freak out and think you're doing something wrong because your estimates don't exactly match the author's.